the 2022 Oskar Klein Memorial Lecture. We're very happy to be able to host the lecture in person this year after a hiatus due to the pandemic. And the lecture is in memory of Oskar Klein, who was a very prominent Swedish physicist and a long-time faculty member at Stockholm University. Now, Klein received his doctoral degree in 1921 from the University College of Stockholm, which was the precursor of Stockholm University. In his early career, Klein worked with Bohr in Copenhagen, with Ehrenfest in Leiden, so he was active in the very important period of physics in the early 20th century. He was briefly on the faculty of the University of Michigan in the mid-1920s, before returning to Europe and Sweden, where he was first at Lund University, and then from 1930 onwards he was professor of physics at Stockholm University. Now, Klein actively participated in the development of quantum mechanics, quantum field theory, and made a number of lasting contributions to theoretical physics, some of which are listed here. And I don't think I will go into them, but some of them will also feature in today's talk. Now, I'm also, well, I'm very happy to introduce today's speaker, Igor Klebanov. Igor is a key contributor to modern theoretical high-energy physics. His work covers a broad range of topics in quantum field theory, string theory, on the physics of hadrons to supersymmetric gauge theories, to black holes and their higher dimensional generalization, and black rays. Igor's work on the dynamics of so-called Dirichlet rays in string theory laid the foundation for the celebrated ADS-CFT, or H-gravity correspondence. And his landmark paper with Oskar and Klein gave a precise definition of this correspondence. It's really useful, because really turned it into a very versatile tool for calculations, which has had a profound impact on the field over the past 30 years. Igor was born in 1962 in Kharkov, in Ukraine. He moved to the US as a teenager. He received his bachelor degree from MIT in 1982, PhD degree from Princeton University in 1986, and then, following a 3-year postdoctoral appointment at the Stanford Naval Accelerator Center, California, he returned to Princeton, where he has been since. He's currently the Eugene Higgins Professor of Physics and the Director of the Princeton Center for Theoretical Science. Igor has received various honors over the years. In 2010, he was awarded a Guggenheim Fellowship. He was elected to the National Academy of Sciences in 2016. He received the Thomas Rogner Prize in Rome in 2014. Pomeranian Prize in 2017, and today he will be awarded the 2022 Oskar Klein Medal. And for that, I will yield the floor to my colleague Niels Overs, Director of Medica, who will present Igor with the medal and chair the remaining of the proceedings. Please.
Thanks a lot for this nice introduction. Yeah, then I would like Professor Igor Klebanov to come forward. Instead here. I typed this. It's on screen because I cannot screen as well. But it's really great honor to give you the Oskar Klein medal. It's a beautiful medal. I really hope it finds good home. Great yeah, so now we come to the exciting scientific part. Just one thing before that, as also announced after the talk and after questions, we have a festive reception. We have fantastic weather, so it will be outside the restaurant. So everybody is invited for some bites and drinks. But I think we're all in great anticipation waiting for Igor's Oskar Klein memorial lecture. Yeah. So, yeah, so Professor Igor Klein is going to talk about strong interactions, strings, and extra dimensions. Thank you very much.
Thank you very much, Harris and Niels, for these kind words. I'm extremely grateful for this award and very happy that I was able to actually come here in person. These days, as you know, it's some unpredictable things happen, but I'm very happy to be here. Now I can really tell people that I won this award. And it's a separate question whether I deserve it, but here I am. So this is the first slide of my talk, and I took the liberty to put 3 flags. Generally, I try to stay away from politics, but I really wanted to put these 3 flags, and one is, of course, the Swedish flag, because this is the country of Oskar Klein, and we're here in Sweden, receiving this award from Sweden, and of course the US flag. This has been my country for almost 44 years. I moved in 1978, and this is the flag of Ukraine, almost symmetrical in terms of colors, and these days you see many times this flag included for solidarity, but as Laris mentioned, I have a connection with Ukraine. I grew up in the city of Kharkiv or Kharkov in northeastern Ukraine, which of course has faced a terrible situation over the past 3 months, and I have relatives there from whom I was getting reports. It's been really shocking, and apparently the last few days it's a little better in the city itself, but there is hot war not far from the city. So just, I wish this madness ends somehow soon. It's been absolutely unexpected and shocking situation. But now switching to, so just of course offering solidarity to people of Ukraine and all the good people everywhere. Okay, now on to science, strong interactions, strings, and extra dimensions. So already, first of all, it's a great honor to be associated with the name of Oskar Klein, who had enormous impact in theoretical physics. And his ideas have only grown in importance, I would say, lately. So Lars mentioned some of his key contributions. I mean, to me it's stunning that someone like that was not rewarded with even bigger prizes than he had, because textbook material, Klein-Gordon equation, any quantum field theories lives by this, and so on and so forth. But one of his ideas that's been very much used is the idea of extra dimensions, and in particular he wrote a paper on extra circular dimension and tried to talk about how it's stabilized by quantum effects. This is, of course, this Kaluza-Klein unification of Einstein's general relativity and Maxwell's theory of electromagnetism. And this is a very well-known work, but I learned from the proceedings of the centenary conference of Oskar Klein that he also had a conference talk in Warsaw in 1937, where he also included momentum modes around the circle, and came close to formulating the Young-Mills theory. Now, following this idea of extra dimensions, Pauli actually contemplated 2 extra dimensions curled up in a sphere rather than 1 curled up in a circle. And this leads to basically to a non-abelian gauge theory with orthogonal gauge group O3, which is just a symmetry group of rotations of the sphere. This is also unpublished work, and it appeared apparently a few years before Mills. And now there are various modern extensions of the Kaluza-Klein idea of extra dimensions. In particular, there are so-called Freund-Rubin compactifications, which involve a negatively curved space times a positively curved space. And he considers space times a sphere. And these turned out to be key elements of the ADS-CFT or ND-de-Sitter conformal field theory correspondence. So in this way, Oskar Klein was really a pioneer of geometrizing gauge theory, which is some of what my talk will be about. By the way, feel free to interrupt. Let's make this informal. And there are different topics in my talk, so I don't want it to be all sort of merged together. But let me just talk a little bit about string theory and strong interactions. So one often hears of string theory as a kind of theory of everything, unification of absolutely everything, and some people make fun of string theory in this way, but it is basically the only solid candidate for a quantum theory of gravity, it appears, at least in sufficiently many dimensions. Well, I mean, not too, because now there is a lot of work on two-dimensional quantum gravity there. You can just, seems like you can just do the path integral of quantized gravity, but it gets much harder in 4 dimensions. So what would the ultimate theory look like? It would include the standard model, namely strong or nuclear interactions, electromagnetic, weak, but also include quantum gravity into one consistent quantum theory. This, of course, is very, very hard. It's such an ambitious goal. I would not be surprised if hundreds of years from now we're still doing this. I mean, in the 80s, there were high hopes that it would be all like sort of delivered in a nice package with a bow and top. But it hasn't happened yet, and now there are all these debates about what is this string landscape versus swampland and so on. But actually, string theory had sort of more humble beginnings, which are still, to me, extremely ambitious. It was invented in the late 60s to model the strong or nuclear interaction. Now, these interactions are basically hard to, this is really physics, and this is what binds nuclei together. For example, we know that nuclei have protons and neutrons, and the protons, of course, repel electromagnetically rather strongly at these short distances. So what keeps them together is the strong interaction, which is a very powerful glue that sort of holds us together. So in the 50s and 60s, people were discovering many new particles, and so it started with pi meson and so on, but then it went on to many particles, and so the strongly interacting particles are called hadrons, and adros means heavy, I think, in Greek, to distinguish leptons or light. And this is, for example, a bubble chamber picture where a charged K meson decays into 3 charged pi mesons. So the K meson comes in with this red color and then three green colors. And charged particles are always easier to see because their trajectories bend in the magnetic field. Right. So as I already mentioned, there are 2 types of hadrons. There are baryons, like proton and neutron inside nuclei, and then various other types of baryons that include, as we'll see, flavored quarks and so on. And then, it became clear at some point that baryons basically contain 3 quarks, plus other stuff. And mesons contain a quark and an antiquark, and this would be the pi meson, k meson, rho, then things like J psi, and so on. And so the strong interactions have very short range, around 1 Fermi or 1 femtometer, 10 to the minus 15 meter, which is the characteristic size of the nucleon. But they're really roughly 100 times stronger than electromagnetic interactions, and in this way can keep nuclei together. So without strong interactions, there would be no world as we know it, really. Okay, so now the substructure of these hadrons, as probably all of you know, in the early 60s, Gell-Mann and Zweig realized that the multiplets of kaons and mesons and baryons look like they can come from 3 types of quarks, up, down, and strange, right? And here you can see the octet of mesons, and you see an octet of baryons, and then there is a 9th one, which is a singlet. This was before the heavier 3 quarks were known, the charm, bottom, and top. And this neat picture was realized, I think also Neyman played a role in this. And so we see this SU3, approximate SU3 symmetry. It's broken because these objects, of course, don't have the same masses. But strange quark is still sufficiently light that you can distinguish these multiplets. And this was basically before people realized that quarks can come in different color varieties. It was just a phenomenological model, but a tremendous breakthrough for high energy physics. But then people started discovering heavier mesons with higher intrinsic spin. For example, these are spin 1 mesons like K star, omega, rho, and so on. And then at some point, Regge trajectories where it was realized that if you plot the spin versus the mass squared, there are some linear relations. Now, I have to apologize to Paula for reviewing the history of something that I didn't live through, so maybe Paula can correct me. But basically, that's still, in a sense, this linearity of Regge trajectories is perhaps the biggest sort of physics evidence for the existence of strings in the real world. And here, what I plot is the leading Regge trajectory of mesons of isotopic spin 1 mesons, like rho, A2, and so on. And you see definitely some linearity. And now what about these other ones? Well, they, in addition, we'll see that they contain some additional vibrational excitations on top of the rotation. And of course, this is how string theory was born. So in 1968, Veneziano, based on earlier work by Rubinstein, Versoro, and others, proposed a very elegant formula for the amplitude of elastic pion scattering, which is just a beta function. These are the Euler gamma functions, and these S and T are kinematical invariants in 4-particle scattering, and his formula, there are exactly linear Regge trajectories. Alpha of S, there is some linear relation where alpha prime is called the slope and alpha of 0 is called the intercept. Yeah, here I'm being very brief because it's not really a string theory colloquium, but essentially the idea of quantum string replaces, say, a point particle decaying into 2 particles at the local vertex by an open string splitting somewhere in the middle into 2 open strings. And this is a kind of smoother process. So it was, during the couple of years after Veneziano's paper, it was realized that this amplitude has string interpretation. But this specific theory has some problems. There are some particles with negative mass squared. This is what's called the simplest bosonic string model, the Veneziana model. It really wants to live in 26 dimensions rather than 4 dimensions. So it was a nice attempt, but it hasn't truly explained strong interactions. In the meantime, just a few years later, quantum chromodynamics emerged, which is now believed to really be the exact theory of strong interactions. And it's based on the idea of color, which already emerged even earlier. So each flavor of quarks comes in 3 colored states. And now the color symmetry is exact. Namely, these 3 colored states. It's not only exact, but it's also a local gauge symmetry, which requires introduction of mediators of the force, which are 8 colored gluons in the joint representation of SU3. It really, in the real world, it really is SU3. I mean, there are some ideas on the fourth color, but that would not be an exact symmetry. And here is the Lagrangian of QCD. Sorry for this formula, but it is something that people sometimes put on T-shirts, right? It's one of these amazing equations that is both compact and describes real world on the nose, not just approximately. So here you have these quark fields psi with color label and flavor label, and A mu are the gluon fields. There is the non-abelian generalization of Maxwell electromagnetism action, and this is the field strength. So basically, very compact theory. And so why, question? So why were people so sure as early as 1973? I think this was sort of germinating, well, I don't know the history, but apparently Gell-Mann's talk in 1972 was very important for he has this legendary paper called The Advantages of Color Octet Gluon. But I think what solidified its status is the discovery of asymptotic freedom, namely the fact that this interaction strength, which is this is G sub S, is the Yang-Mills analog of electric charge, and it actually, if you compute how it evolves with momentum transfer scale, you see that alpha sub S, which is G squared over 4 pi, actually gets weaker at short distances. And this is called the asymptotic freedom. Was a tremendous discovery in 2 independent papers by Grossen, Wilczek, and Politzer, published in 1973. And this, of course, was honored by the Nobel Prize in 2004. Took quite a long time, but I think the case was clear even much earlier. So this is what QCD is, and it's a kind of perfect quantum field theory, because it can be separated out from the rest of the standard model. You don't need weakened electromagnetic interactions to mix in with it. If you just literally take this equation that I showed on the previous slide, it stands alone. And because of the fact that the coupling goes to 0, really at shortest distance scale, means that the theory can be defined non-perturbatively. And there are also, people have discovered the lattice regularizations of this theory, which really allow to do calculations even in the strong coupling regime, but they're numerical calculations. So this curve here matches the analytic calculation. So Grossen, Wilczek, and Politzer calculated the one loop running. Then a year later, there were some 2 loop papers, in particular by William Caswell at Princeton, who sadly died on 9/11, actually. And he also discovered this Caswell-Banks-Zaks fixed point, actually, as a result of. Now people have gone to, what is it? I think 5 loops, but so you really can do this 5 loop running, but the difficulty is that this sort of idea even of the running coupling kind of breaks down at the scale of around 1 GeV, where the sort of formally, if you continue this coupling, it's just going to blow up. And this is, at the scale at which it blows up is called lambda QCD. It's the QCD scale of around 200 mega electron volts. So just these perturbative calculations are not good enough in the true sort of long distance regime. Long distance compared to Fermi. It's short for most purposes, but long distance for QCD. So in particular, there is the confinement problem. Namely, why are these colored quarks and gluons not observed as asymptotic states? And this was a question that was asked from the beginning, really, because in particular if you look at this action for QCD, right? And suppose you just throw away the quarks. You don't need the quarks. You can just have a pure glue theory with this action, right? The quarks, these gluons, the gluon fields propagate at the speed of light. But in real world, we don't see any free gluons. That's in a nutshell and first, it's actually interesting to read papers from that era, because first people thought maybe there is some kind of Higgs mechanism that has to be applied to make them massive. But once you add the scalar fields, then the theory ceases to be well-behaved and ultraviolet. You no longer have this nice asymptotically free theory. So that threw out the idea of Higgsing. So unlike electroweak interactions where there are Higgs fields, here there are no Higgs fields, so something else has to happen. And people doubt this term, the color confinement, or like that somehow these quarks, the colored quarks, are permanently confined inside hadrons. And from even when I entered the field, I remember people were complaining, is this physics or is this philosophy? If you can never see a free quark, is this really a physical concept, and so on. But of course, and there was actually interest from philosophers in this question, but already by then actually the situation was very clear, and that quarks are physical objects. And this really, I think there was this so-called November revolution of 1974 when the J-psi was discovered. And it was very clearly a CC bar state. You could really see like the heavy quarks moving in some potential. And now people very routinely see the quarks propagating some distance in detectors. In particular, the B quark propagates some appreciable distance. So it's clear that at very short time scales, quarks are not confined. They really live and move like free particles, but then they kind of get dressed up and get confined into colorless objects. And so this is a picture of a process where some free quarks and gluons initially fly out, and then they turn into actual found states. So all of this is very complicated, and there is a code word for it, the confinement problem, which is only partially understood. And in fact, around the turn of the millennium, the Klein Mathematics Institute has come up with a set of problems for the new millennium. And this was actually problem number 1 listed. It's called the Young-Mills and mass gap. And basically, the mass gap just means that even though naively you would say that there is a free gluon running at the speed of light, a massless particle, in fact, the physical states, there are no massless physical states, there are only massive physical states. And this is still listed as unsolved. Okay, so any questions or comments? So this, of course, the popularity of this problem kind of rises and falls, oscillates a bit with time. But here is some news that coming soon there will be a Simon's collaboration on confinement and QCD strings. of which I'm part of, we're actually setting up this logo and so on. And we, a group of people, including me, applied to the Simons Foundation, and it looks like we've been selected. It's still not funded fully, but hopefully will be. And we would like to sort of revisit this problem with new tools, like a combination of tools, including sort of thought experiments, real state-of-the-art computations, and also input from real world, because at LHC there actually have been a bunch of new and unexpected strongly interacting particles discovered, which are not fully understood. So we will have this confinement collaboration, which people are asking me, are you going to prove confinement? I really can't promise that, but I hope we'll do something good, at least. The Simons Foundation expects us to work hard now. So what do we know about the confinement problem? Well, so when Wilson set up the lattice action, already within a few years from that, people were fairly sure that there is color confinement. So this is Wilson's action. You basically have a bunch of links, and on each field there is, say, an SU3 variable u, and then you're just supposed to do the integral over all these SU3 variables. And there is a famous criterion for confinement, that the Wilson loop has an area law rather than perimeter law. And if you work out the strong coupling expansion, this is extremely hard to do in the continuum, but on the lattice, you're just expanding in this action term. And it turns out that if you take the Wilson loop, which is just a product of links around some large contour, at leading order, you have to basically fill this large area with individual plaquettes. And then you kind of fill this sort of rolled sheet of a QCD string with these plaquettes. And unless you fill it in, then it just gives a vanishing contribution, because the integral over u itself is 0. So for each link, there has to be a link running in opposite direction. So integral of u ij, u dagger, kl is non-zero, but the integral of u itself is 0. So people realized, they started doing these strong coupling expansions already in the mid-70s, and then you see that in the strong coupling limit, you see this area law, namely that the expectation value of Wilson loop is the exponential of the area times some function of g. But then the key question is, this is extremely far from the continuum limit. So instead of taking g to be very large, at short distance scale by asymptotic freedom, you have to take it very small. And the question is, can you do this? And this is the main difficulty of the proof. Can there be some kind of a transition in behavior where you lose this area law behavior? I think the numerical simulation strongly suggests that the answer is no, but there is still no rigorous proof. And so back in the 70s, I think people worked with very small lattices and saw some suggestive signs. But lately, there is an explosion in computing power. People can now have 4 torus with basically 100 lattice sites in each direction. And I'm told that this can improve even much more. This is in pure blue theory without fermions. So you can really do precision calculations. You see the matching to asymptotic freedom very well, and then you can compute basically exactly what is the coefficient of this area, which is called the string tension, and so on. So this is the type of pictures you can do from the lattice. You put, say, a probe heavy quark and an anti-quark, and then you see that the action density gets sort of collimated to this string-like region. And its characteristic thickness is again around the Fermi. So this is very different from the dipole pattern that you see in electromagnetism. So when the quarks are really close together, you will see a coulombic force, but then it should change over to the linear force due to this mysterious confinement mechanism. But in any kind of rigorous sense, it has not been proved. What people do is they try to fit these properties of this string to the relativistic string action called the non-Bugota area action with corrections. And so one, besides proving confinement, it would be extremely interesting to understand more precisely how these strings behave. What is the action governing them, and so on. Okay, so now if so, you see that the high spin mesons are described by, say, a quark and an anti-quark moving with high angular momentum with this UCD string stretched between them. We know that in real world, the energy density of the string is around 1 GeV per Fermi, which translates into 1.6 kilojoules per centimeter. So that's a lot of energy density. But in real world, we cannot really stretch the string out because the dynamical quarks will break the string. There will be quark-anti-quark creation, and the string will break into two strings and more than that. But in a hypothetical world, we can just remove the light strings. We can only have light quarks. We can only have heavy quarks. Then you see this linear behavior, this confining behavior. You can see it to very long distances, and people can study it very actively. And then another sort of even more interesting thing is, what do baryons look like? The baryons have these so-called white junctions, or string junctions, and this is also a picture from the lattice about this white junction. So as you stretch them out, like for example, if they start spinning, each of these strings will elongate, but there will be some energy contained in the white junction. And precisely how much energy is apparently very important for the phenomenology of some of the new states that were recently discovered at LHC. So an improved understanding of these objects is also important.
Can I ask quickly?
Yeah.
Can one also get the spectrum of these states from some effective QCD string?
Of the junctions?
Yeah.
Well, one thing, people can estimate how much extra energy it gives. Usually when people construct phenomenology of these tetraquark states, the tetraquarks actually contain the white junctions. And I've heard talks where people just put in phenomenologically some amount of energy to fit it. But I think a lot less has been done for matching the lattice results with compared to the usual QQ bar mesons. You know, so this is kind of the frontier now for these things. Another thing about these three string junctions is, like when we talk about the large MQCD, which I was gonna do next. By the way, how much more time do we have?
Certainly 20 minutes.
Okay. So the other idea which emerged in the 70s is this large N idea, where instead of three colors and SU3 gauge group, you take N colors and SUN gauge group and take large N limit, keeping Gn mil square times N fixed. Then, as Hooft realized, you only have so-called planar Feynman diagrams. And for example, here is an example of a planar. This is a 3-gluon vertex, but you have even the planar diagrams are very hard to study, but it still simplifies things nicely. So many people feel that if we can't solve the SU3 pure blue theory, it should be somewhat easier to solve the SUN theory. And the reason is that because the splitting and joining of strings gets kind of suppressed at large N. So you can talk about a free string of large N QCD. And this should be sort of one of the first goals of I was actually at an event in honor of David Gross 2 days ago, and someone reminded them of a talk by Ed Witten in 2001 that said, I'm still not finished with the homework David suggested for me, which is to solve large N pure glue theory. So this is sort of problem has been around, but it's still basically not fully solved. But in the meantime, there has been tremendous amount of activity on these type of issues, not within sort of pure glue not supersymmetric theory, but basically in some toy models or related models where you can do a lot more work and find exact results. And this started in the mid-90s due to the work of Joe Polchinski, who realized that there are objects called D-branes within just the fundamental 10-dimensional superstring theory. And on these D-branes, if you stack n D-branes, you realize SUN gauge theory, but it's a maximally supersymmetric gauge theory. It has these gluons, but it has some other additional particles that in some sense simplify the theory. And these D-branes curve space and create this region of space. So this is the exact curve metric of these branes. And as you approach the branes, you get a kind of Kaluza-Klein region, which is 5-dimensional anti-de Sitter space, negatively curved space, and 5-dimensional sphere. So you can see the 5-dimensional sphere at small r pretty easily because this is the metric of 5-dimensional sphere. If you look at this factor here at small r, this behaves like L squared over r squared. It cancels this r squared, and you just get a 5-sphere of radius L. And it turns out that this radius L of this space becomes very large at strong Hopf coupling. So it's a bit of a miracle, but you can essentially map the calculations in this large N super Yang-Mills theory to gravity on ADS 5 process 5. Namely, we have a kind of Kaluza-Klein compactification of 10D supergravity on a 5-dimensional sphere. And this actually people studied even before the 90s. There were very careful papers in the mid-80s studying the full Kaluza-Klein spectrum of this theory, including all the excitations of the 5-sphere, for example. Okay, and this all matches very nicely, and now there is a code name for it, this ADS-CFT duality. It actually gives you access to a whole new information at strong coupling. And this is a kind of joking picture of the hyperboloid. The reason so Juan Maldacen and I wrote a kind of non-technical article, and the reason we put in cows is because it's the spherical cow joke, right? Spherical cow is like an idealization of reality, but here we wanted to call it the hyperbolic cow because this is a hyperbolic space. And this is a 2-dimensional sort of hyperbolic disk. You see that its radius is really infinite because you have to think of each cow being of a fixed size, so you fit an infinite number of cows at the boundary of this disk. So this provided a whole different outlook on this non-perturbative region of strong coupling. While at weak coupling you can develop these so-called Feynman diagrams and expand in powers of g squared n, suddenly you can use this ADS 5 process 5 space to expand in inverse powers of this coupling. And lots of work has been devoted to matching these two expansions and to checking that they really describe the same functions. And for example, Joe Minahan and Konstantin Zaremba, who are here, did breakthrough work on this kind of matching for N=4 super-Reynolds theory. But this is all, so this, you can just say it's a cousin of QCD. And some people describe it as a close relative, to some it's a distant cousin, but it certainly differs in the sense that there is no asymptotic freedom in it. The coupling just stays constant with scale. You don't see this weakening of the coupling at the scale. And this also manifests in the fact that this theory does not exhibit a linear confining potential. There is a method for computing the potential between quark and anti-quark by placing them at the boundary of ADS space and connecting them by a string, and you get the potential which is exactly coulombic, 1 over r, basically, at any coupling strength. And in particular, at strong coupling, it's root lambda over r. So but suppose we really want something confining, what do we do? Well, phenomenologically, you can, and this has been a very popular set of models, which I think initially were pointed out by Polyakov. You need to put in some modification of space at this so-called infrared end, or put in a kind of wall, which deforms the anti-de Sitter metric to something different. Basically, the space should end. So this is the sort of metric of ADS space. The boundary is at z equals 0, but at large z, the space must come to an end, and the string does not lose its tension. So then the string will just go to the boundary, and you identify this fundamental string at the infrared end with a confining string, and you can compute its tension. And this seems like a cartoon, but there are models where you can really follow this through, from sort of fundamental construction of 10-dimensional string theory. You can construct sort of more complicated models. This I will just flash by, but this is the work that maybe the work that I'm most proud of that I've done. There are modifications of this anti-de Sitter type metrics which really exhibit confinement. And they're sort of very natural from the point of view of supergravity. They consist of some Calabi-Yau space, which is called the deformed conifold, that looks like this, and then it picks up a warp factor h of y, in such a way that the string really makes a transition from the coulombic behavior to the confining behavior. And then it's a very simple calculation to compute in this metric this transition. You can compute the QQ bar potential. It's coulombic at small r and makes a transition to linear at large r. And this calculation is sufficiently easy that actually an undergraduate student did this calculation. And for comparison, this is the lattice calculation of the same effect. You can really see some qualitative similarity, but this is of course purely numerical and took many, many hours of computer time to perform, but people are now sort of improving this. So this at least shows that there are these models starting from 10-dimensional string theory which have this transition from coulombic behavior at short distances to linear behavior at long distances for the quark-anti-quark potential and incorporate color confinement. Okay, so this is sort of the general range of questions, but it's also fair to say that the problem is this doesn't fully solve the problem. I mean, it shows that confinement is really present using this set of tools or that set of tools, but that's why we need a confinement collaboration to sort of revisit everything. Like there were all, basically people are not sure what is the mechanism of confinement in different models. There are suggestions, I don't know, monopole condensation, instantons, this, that. There is no full agreement, and I think people lost focus on this. for many years. And so just in the last 5 minutes, I wanted to talk briefly about something I've been doing, also like going back to some of the things I was doing earlier, which is going back to simple models in one spatial dimension. Now, in one spatial dimension, the Coulomb potential actually is linear. So the confinement is automatic. You don't need to do anything non-perturbative to see confinement. You just solve the equation like box Laplacian squared phi, not Laplacian phi equals delta function, and you get this sort of linear potential, absolute value x. So you would say that basically any gauge theory you write down in 1 + 1 dimension will be confining, and this was the assumption. And actually, one of the classic models of confinement is the so-called Hopf model, which is two-dimensional QCD coupled to quarks. The beautiful thing is that this model at the large n limit can be solved using so-called light cone gauge, and you get a singular integral equation. So x is the light cone momentum fraction. You get this kind of equation, which you can then solve numerically. It's still not analytically solvable. So even here, you need to do some numerics, but you get these so-called linear edgy trajectories of mesons. And in this case, they're not spinning, right? Because there is no dimension for them to spin, but they're like vibrating states. And you see that n is like a vibrational excitation number, and you see asymptotic linearity of these trajectories. But this toy model does not really have any dynamical gluons. So it's maybe too simplified to tell us something about QCD. And what I started doing already 30 years ago, with the Princeton postdoc Simon Dowie, he was a postdoc at the time, we simply added by hand a joint matter. And you can either add an adjoint scalar field or an adjoint fermion. And actually, the simplest model is where you put in an adjoint Majorana fermion, and you write down this very simple model. It's actually, the model has no real divergences. It's basically a finite model. And the question is, what is its dynamics? It turns out that this model is sufficiently non-trivial in itself that it's still not completely clear what's going on with it. And there were some debates lately, but the mass is sort of not renormalized, and the m = 0 value is protected by some symmetry. So there is no real shift of mass. And it turns out that at this m = 0 point, the model loses its confinement. There were some debates about it, but it really appears certain now. In some sense, the string tension gets screened somehow by these gluinos. And that's still like rather surprising phenomenon. And recently, I wrote a paper on a somewhat more complicated model where, in addition to a massless adjoint Majorana, you add massive Dirac fermions. And this was with Ross Dempsey and Silvio Pufu at Princeton. So we have two sets of fermions. And in this model, we can study this sort of, the mesons start looking much more complicated than in the Hopf model. In the Hopf model, they're just bound states of a quark and anti-quark. But in this model, there can be also a lot of different adjoint quanta kind of forming a string. So you have a quark on one end and a quark on anti-quark on the other end. And in between, you can have basically, say, 2, 4, 6, any number of pairs of these adjoints. And then you can study what happens with this spectrum. And then it turns out that these quarks can get liberated in some sense, rather unexpectedly. And they can, in other words, the spectrum of mesons, unlike that in the Hopf model, where it goes equally spaced and discrete forever, here it becomes continuous above a certain threshold. And we saw it by computing the spectrum of these more complicated mesons. And what it points to is that this QQ bar potential flattens at infinity. It starts out linear at short distances, but at long distances it kind of gets screened by these massless neutrinos. And there are some more mathematical papers pointing out that this is due to some non-invertible topological symmetries, but we see it just from sort of the old-fashioned spectrum computation. On the other hand, for when you turn on a small mass, then this exactly flat asymptotic form becomes linear with a small slope. And the string tension sort of becomes proportional to m. So then you get a model of very weak confinement. So this seemingly very simple two-dimensional model still is not fully solved. So, and then there are related models that condensed matter people are interested in, related to one-dimensional chains, or maybe they can be simulated using atomic traps. So there are various sort of points of interest in these kind of old-fashioned models that are still not understood. Okay, so let me then, so what's the lesson from these last 3 slides? Is don't take confinement for granted. Even in 1+1 dimensions, where confinement seems trivial, and you would naively say that you cannot screen, say, a fundamental charge by an adjoint one, something mysterious happens, and you can screen the string tension exactly to 0. What if something like this is possible in higher dimensions? That would be a huge surprise. I don't think there are... So basically, I think it would be great to revisit all this circle of issues, and in particular, point out what sort of understand confinement and different mechanisms in 1+1 dimensions, 2+1, and 3+1, and also improve connections between these effective emergence strings that you see on the lattice and the full machinery that has been developed for the fundamental strings and superstrings. Perhaps the most provocative question is, can we solve, in some sense, large M pure glue theory or related theories? This seems extremely hard, but people are making a lot of progress in sort of extrapolating lattice results to larger N, and there could be some miracles there that have been completely overlooked, I would say. And in particular, the numerical results are getting much sharper, and we're told that with machine learning techniques and improved hardware, we can expect like extremely fast progress in lattice theory in the next, say, 10 years. So I think, I hope I convinced you that sort of the original home of string theory, namely with strong interactions, is still a good home, and there is a lot to be learned from that. Thank you very much.
Thanks a lot for this. Thanks a lot, Igor, for this beautiful and extremely inspiring lecture. We have time for questions. I see Hans, but wait, I'll come with another microphone.
Thank you, a very nice talk. You speak here about 2+1 dimensional QCD. There is some very interesting work by Parmesan Nair and Dimitra Karabali, where they use conformal theory methods, and they calculated the string tension and also approximately the mass gap. Do you have any comment on their work?
Yeah, I'm aware of this work. I believe this was from around 20 years ago, right?
Yes.
Yeah, they had a certain ansatz. I can't make any in-depth comments because I remember discussing it back then. Roughly speaking, they were trying to do strong coupling, take strong coupling limit directly in the continuum. I think there were definitely some questions whether that's rigorous or not. But I think their results were in principle testable numerically. This is actually one thing I would like to think about again.
Yeah,
For example,
I think
they made some concrete predictions from multi-string tension.
I think that, first of all, the basic insight was that they managed to factor out the gauge volume. So they had a description in gauge invariant variables. And also they compared the string tension with the numerical calculation by Tappert. And they had an expansion. So they first had a pretty good agreement, and then they calculated the next contribution, and they got a better agreement. So that looked pretty promising.
Right. Yeah. It could well be. Yeah, I'm not sure it fully proves it, but it was even quantitatively quite good, if I recall. Maybe my recollection was that in some cases they agreed. There was also a question of not just a single string tension, but what happens, for example, with the doubly wound string or triply wound. And you know, there are these, and another, this is actually on my slide, it's multi-string tension. Then, for example, if you take two quarks in an antisymmetric and two anti-quarks in an antisymmetric, how that string tension differs from, it's not just a sum of two elementary string tension. And I don't remember if their theory passed that test completely or not, but because people argue a lot about what is the K dependence of this K string tension. But I mean, I completely agree that this was one of the better continuum attempts to get QCD under control and two dimensions.
Because they got the Casimir energy correct also, actually.
Yeah, I think the Casimir, it was, I think they predicted exact Casimir scaling. I think, but from lattice, I thought it falls somewhere between Casimir and sine law. Like there was no. But this
I didn't mean the Casimir scaling on the string tension. They calculated the Casimir effect that is putting.
Oh, the Lusher term.
Yeah,
the Lusher. Yeah, no. I think it's definitely very interesting work, and thanks for pointing it out.
Other questions? Maybe I can ask questions. So the point you mentioned there, the third bullet, to improve connections between the more technological QCD string and the fundamental string. Do you have any further thoughts on that?
Well, I think that there was for example, in these top-down 10-dimensional models, there we say just a string that sits at the bottom of this warped throat is basically so their fundamental string equals QCD string. And then you can start computing basically what are the extra massive modes on the QCD, because then the string is not purely going to be governed by Nambu-Goto action. There are some additional massive modes and so on. And this is actually, from lattice now, people are pretty sure that there are some additional massive modes on the string. So it's not purely Nambu action, there are even resonances. And so there are some results just from the bottom up, kind of just matching lattice calculations. But we don't have the full string kind of two-dimensional theory describing the string.
But what I take from you, the holography might be the most promising route towards that.
I'm not totally sure of that. I mean, it would be great to apply holography to this question more I mean, we do have like applications of holography to these types of models, but if you give up on supersymmetry or go to the asymptotically free regime, we don't really have exact holographic models. So that's why I think it would be like, if we can find a holographic model, terrific, but I think there should be different possible tools.
Yes.
You mentioned in passing some new results from CERN. Can you elaborate on that?
Yeah, thank you for this question. Yeah, I didn't have slides on it, but there are these so-called exotic hadrons that have been, ever since Gell-Mann wrote his paper, he pointed out that it doesn't have to be just Q, Q bar. There can be Q, Q bar, Q, Q bar. And these things have really been discovered. In particular, within the past year, there is a so-called doubly charmed tetraquark. There is chalk I can write down. So there is this object that people call TCC plus, and its quark content is basically CC U bar D bar, and its mass is extremely close to the D star threshold. Where D is basically Cu bar, right? It's a heavy. It contains one heavy quark charm and a light antiquark, and D star is a vector one of this kind. And so this was actually predicted in some sense by. In particular, John Rosner and Mara Karliner have some interesting estimates of this. But this type of flavor content cannot come from just a regular meson. So you can think of it as a kind of bound state of two mesons, maybe, or it's a tightly bound Q, Q, Q bar, Q bar. And this is sort of one of the pretty hot topics in phenomenology of hadrons that people are talking about. And actually, the reason these baryonic junctions are important is because when you draw this picture, the CC quarks are very close together, but then there is a kind of junction going into U bar, D bar, and there is this white junction. I think that's a popular picture of how it could be built. This is very complex. The mass of this meson is very, very close to the threshold. So it's a very narrow, easily identifiable state. There was quite a lot of press about this particular state. And now the search is on for similar things with B quarks that are much harder to find. Because if you replace the C by B, then the belief is that they will be really tightly bound and cannot decay at all, except weakly. They will not be able to have strong decays. So there is kind of new life. This is discoveries by LHCb, which is sort of more of a detector for B quark dynamics. It's not one of these huge high-energy detectors, namely CMS and Atlas. It's a smaller collaboration, but they've had quite a number of discoveries of this nature that kind of add to the relevance of strong interactions at the moment.
Okay. Questions? Yes.
Thanks for a very nice talk. I have a question about sort of part on distribution functions. If I think of, say, the proton as containing also other quarks than the valence quarks, so maybe it contains a little bit of anti-down quark or strong quark. So in these models, or this picture, that you showed, maybe the y-junction picture, for instance. Is there any way I can understand from that where, can I get some information about partial distribution functions? Can I get some information about other core content?
In holographic models or in the... Because what I talked about at the end is literally those distribution functions in the light cone frame. For example, so I was able to solve two-dimensional QCD. I mean, I was rather brief on this, but this phi of x is exactly the Parton distribution function. Because x is the momentum fraction carried by a quark, and 1 minus x is the momentum fraction carried by the antiquark. So this phi of x is, the state in the light cone frame was something like, people work with these light cone wave functions, and they have integral dx phi of x. X runs from 0 to 1 because it's a fraction, and then you have say B dagger, that's the creation operator of the quark, with momentum x times p plus, and B dagger x times p minus, acting on the light cone vector. So you just get a two-body state, which is like Q. So this creates a quark, and this creates the antiquark. So in these light cone approaches, they just really produce these functions. And then in this model that is more complicated with the joints, it gets more complicated because instead of just one momentum fraction, there are many momentum fractions. And the state is a mixture of a state with, say, 0 adjoints, 2 adjoints, 4 adjoints, and so on. It's hard to solve exactly, but you can still numerically get some information on the wave function of this. Now, for QCD, people have been, of course, trying similar things for many, many years. There you get bogged down in all kinds of divergences and the needs for normalization, and the fact that this light cone approach is a bit asymmetrical and non-covariant. But that's sort of another direction where people hope to learn more.
Maybe time for a last question. Otherwise, maybe I have one. Yeah, so first of all, it sounds very exciting with the new science collaboration on this important problem. So also congratulations with that. I was wondering, maybe you looked into it. Once one has a proof for a Millennium Prize #1, who actually decides what a proof is? Is it a serious, like, is it the community, or is there a panel appointed that will?
I imagine if there is a serious claim of the proof, probably the Clay Foundation will appoint. I think my impression is that there is this more detailed write-up of the technical write-up of the problem, which is longer than this paragraph that I displayed. I believe it was written by Arthur Jaffe, a mathematical physicist, and Edward Witten. And they wrote it back like more than 20 years ago. I think for some strange reason there haven't even been claims of a proof. I imagine if suppose someone comes up with a sufficiently plausible look, they will probably appoint some committee.
I think that's what they did with Perlman, right? I think that's what they did with the Mark Gray problem.
Okay, so well, I really hope that this collaboration will get to the. Okay, that's maybe a very good point to thank Igor Klein again for this fantastic.
Thanks again for this unexpected honor.
Great pleasure to meet you.